All right, so here we go with our absolute zero demonstrator real gas demo. So I hope this keeps it real for you. All right. So any case, what I have here is an absolute zero demonstrator, and it's nothing more than a Gauss meter, and it's got a nothing more than a pressure reading. And if I try to read this pressure reading here, and this is in pounds per square inch, I get a little less than that. So I get, if I look carefully, I'm getting 14.6. Okay, so I'm getting 14.6, and the unit here is pounds per square inch. So lbs per inch squared is the unit here of pressure. Standard pressure is 14.7 pounds per square inch, which is equal to 760 torr, 760 millimeters of mercury, 1 atmosphere pressure, or 101.3 kilopascal. So kind of makes sense that I have something here that's near standard pressure since we are in standard pressure. Now, if you can't see, open your eyes, but if you can see, okay, maybe it's because here, this is reading the pressure on the bottom of this flask. And this flask right here, or I should say flask, I should just say steel sphere, okay? Can't say ball in high school. So this is a steel sphere, and this is a fixed volume. So we have a volume that's constant, and we have the number of moles a constant, so pressure and temperature should be directly proportionate based upon our understanding of kinetic molecular theory. Gases that go faster, okay, will collide more often. Gases that go slower will collide less. Okay, and that should be a direct proportion with Kelvin temperature. So, using PV equals NIT, and using a derivation of that, okay, that we've done, we're going to do what? PV over T equals NI. Well, NR equals a new condition of PV over T. And you can put 1s here and 2s here. But this gives us the combined gas law. PV over T in one condition equals PV over T. Next condition, notice moles of gas are going to be constant in that sphere, and also the volume is sealed. So with that, I can cross off the volumes here. So what do I have, party people, is pressure temperature equals pressure temperature. First condition, new condition. Okay, so I know my pressure is 14.6 pounds per square inch. I'll just leave that alone because I'm not going to change that. The temperature in this room right here is approximately 22.0 degrees Celsius. Okay, and we're going to solve for the new pressure when I pour liquid nitrogen into that container. Okay, now I know liquid nitrogen, its boiling point is negative 196. Okay, we are about 1 atmosphere of pressure, so its boiling point is basically the same. Okay, there is some wiggle room there, but not enough to change what this is about. So we are negative 196 degrees Celsius. Now, the relationship between pressure, temperature, or any temperature-related gas law is based upon Kelvin temperature. We have to know how many degrees away from the real zero. So I cannot use Celsius. Okay, so I've got to convert to Kelvin. And very simply, Kelvin is equal to 273, or Celsius plus 273. I always think of Kelvin as starting 273 degrees sooner, using the what? Same scale as Kelvin, as Celsius. That's why Kelvin doesn't get a degree sign. Okay? So when I do that, okay, so I'm going to solve for Kelvin. All right, so 22 degrees Celsius plus, okay, 273, I get 295. So this becomes 295 kelvins. And again, 295 kelvins means that I'm what? 295 units away from a true zero, where there's absolutely no pressure, no molecular motion. Negative 196, hey, same idea. Negative 196 plus 273, or I'm just subtracting that, however you want to do that. Okay, and you get a 6 here, 16, right? 1, and what's that? No, I messed up. Oh, it should be 77, right?
Yeah, 77.
77, yeah. So that's 77 kelvins. Not degrees kelvins, but 77 kelvins. Okay, so now I'm in kelvins, and I have to be in kelvins in my gas law, and now I'm going to solve for what the new pressure should be. Okay? And if I do my algebra, I know that the new pressure is going to equal to 14.6, and I'll put the units in, pounds per inch squared. Okay. Boy, what happened to this thing? Okay, times 77 Kelvin all over, just doing some algebra, right? 295 Kelvin. And if you notice, party people, Kelvins cancel. I'm left with pounds per square inch. Let's go find that number. Again, this is a derivation from the ideal gas law. So this is a number assuming the gases are behaving ideally. Okay, so 14.6 times 77, okay, and then I divide by 295. What I get is 3.8. 3.81. Let's do 3.8 because I won't be able to read anything smaller than a tenth here. So I get 3.8. 3.8, and that's pounds lbs per inch squared. That is what I expect to get, okay, given the new temperature. Okay, so right now I have 14.6, okay, I don't know if you can see that on the video, but that's slightly less. Okay, so let's pour some liquid nitrogen into this, lower the temperature, and see if our ideal gas law equation, which gives us, oh, Christmas, that's heavy, okay, that gives us the ideal gas law equation, works here. So, using a Dewars flask and a heavy one, I'm going to pour this with liquid nitrogen. I might have to refill it because the container will probably crack. And you can see the pressure dropping. Okay. And there probably is some limitations to going this low with this meter. Okay. I'm going to add some more because we definitely have parts of that sphere, okay, that's exposed to the air. But 3.8 is what we expect. All right, I'm going to fill it some more because there is parts of that sphere that's exposed to a much warmer air temperature. So, okay. Let's tap this because sometimes it gets stuck. All right. So, given that, all right, what do I have now? So I've got let me try to see here. I got 3 point. Yeah, it's a little less than 4. And I'm definitely at 3.8-ish.
Great.
Okay, great demo, right? I'd expect this to be what? Lower, correct?
Yeah.
And I've got 1. That's 4. Yeah, I'm definitely like 3.8-ish. So I'm getting what I expect. All right. And this is not something I'm going to post. Okay. Unless I have the room temperature wrong. I guess 22, but I don't know if that makes a major difference. We were doing so well.
Nord VPN.
I'd like to thank Honey for sponsoring this demonstration.
No. There could be a limitation that this doesn't. All right, well, it probably is now less than 4. All right.
I think we get what it
Is
is.
that-
It should be lower.
Yeah.
Now, I don't know if the fact that maybe there are some limitations in this experiment. So I'm not getting lower than 3.8, but can I think of some possible limitations here? Temperature's 22. I did the math right, okay? What happens to a solid when it gets cold?
Freezes.
It could freeze. It's already frozen though if it's a solid. Does it, think about a bridge. A bridge has teeth in it, if you ever go over a bridge. In the summertime,
It limits the surface area that the liquid nitrogen has.
something, but in the wintertime, the what?
Bridge
The,
expansion.
the bridge does what? Summertime, the bridge expands. And so instead of crumbling up, they give it room. Okay, wintertime, the what? There's constriction, right? A cold object, steel, is gonna get a little smaller. The idea that this container, okay, is what? The idea that this container is staying fixed volume is unrealistic. This volume got smaller. There's expansion due to heat, and there's constriction due to cold. The molecules of atoms, I should say, really the atoms in the metallic substance, the stainless steel container, iron, chromium, are now packed a little tighter because they're not moving as much. They're a little denser. Density is a function of temperature too. So think with me. If the steel sphere is getting smaller, what does that do to my pressure? It increases it. So although I'm getting 3.8, okay, my value is being overestimated because of my volume. So if my volume was to stay, okay, the same size, I bet I would get a significant decrease. But I bet my volume is decreasing, okay, as it's constricting, as the atoms, the nuclei of the metal atoms and metallic bonds are getting more dense. It's making my sphere smaller, which is elevating my pressure, okay? So the volume isn't constant here, all right? So still a good example of thinking about the errors that occur here, okay? And there's probably limitations to this. What I wanted to talk about was why would the pressure, so if that constriction didn't occur, and I can't prove that to you, but what's happening here is by dropping the temperature lower than 183, I'm making the oxygen condense. Now there's about 19% oxygen, so only the oxygen is condensed in there. And if I rattle around, maybe I can feel a liquid. So if the oxygen condensed into a liquid, 19% of the pressure we would expect is now what? Gone. Liquids don't apply a pressure. Okay, so there's got to be some condensation going on here that lowers the pressure. So the fact that I got 3.8, okay, with a sphere that's getting what? Smaller, kind of proves my point, okay? I think. If you can believe that there's constriction there, okay? And if I had a better meter possibly, okay? Maybe it wasn't reading the meter there. But in any case, I'm liquefying the oxygen, okay? And taking away some of the pressure. And that means that we don't have real gas behavior here. Here's pressure, here's temperature. In Kelvin, we'd expect this down to 0 if I can draw, okay? But what's happening is when we get close to the what? Condensation point, which is the boiling point of oxygen, some of that's becoming a liquid and, of course, deviating because the attractive forces that oxygen has for itself, all right? Enough of that. But what's fun, if I raise this up, okay, and I was to pour some water onto that cold sphere, okay, no, it won't explode, but it makes some pretty cool ice crystals. This has nothing to do with the demo. But hey, why not? So this steel sphere is what? Really cold.
Could we
Okay,
smash the bottle?
so
How hard do you think you can draw it?
Maybe a good 70.
No way.
what's it doing to the water?
What if he later?
It's like also.
Yeah, it's making some nice ice right on top of it. And I'm making a mess in front of me. It's okay. So you can hear the ice.
Pour water on the antelope.
Okay, so it's getting ice there. All right,
Ice down.
so maybe a cool demo, maybe not.